the end of the last guided practice, we raised the point that technically we could never have gotten the ice cube all the way up to 37 Celsius because the body would have been below that. If the ice cube was warmer than the body would have taken heat from the ice cube, or at least the water that the ice cube became. So how do we actually solve this more precisely? We're not too far off when we imagine 80 grams of water compared to 90,000 being off by 0.1 degrees Celsius, but this is still not a perfectly accurate equation. But we did calculate out some of the energy that's required to be lost. We know that to melt or to heat up the ice, we're going to need 1,640. And to melt the ice, we're going to need 26,732. The one thing that is affected by the body cooling down is actually right here. The delta T when the ice is liquid. We'd originally said it must go up to 37, but that's not going to really be the case. If our body's cooling down, it's going to go up to wherever the body is. So some of this energy is definitely already called for. We must have this much just to get it to liquid so it can start warming up. But the amount in the liquid phase to warm it up, that's where our change is going to be. Because really what we've got is still that the Q of the ice must equal the energy lost by the body. What is the Q of the ice in this case? Well, that's 1640 joules plus 26,732 joules plus the liquid heating up phase. Mass S delta T. That must equal what happens to the body, which is the body negative of the body's mass, the S, and the body's delta T. Well, we know the mass for both. We know the S value for both. It's the delta T that's actually our unknown here. That's our variable. Think about delta T for a second, though. It is temp final minus temp initial. Now we know the initial temp for the body, that was the 37 Celsius. And we know the initial temp for the liquid, it was 0, coming out of the phase change. Temp final, however, is the one we don't know. We're going to cool down the body, we're going to warm up the ice, but they're going to meet at the same temp, which means temp final is identical for both. And it's the only variable we actually have. Temp final minus temp initial body. And over here, we're going to find that that is temp final minus temp initial ice. This actually lets us calculate out what that final temp will be instead of ignoring the fact that we brought ice up to 37, even though the body got a little colder than that. So let's actually solve it precisely here. If we want to plug in some numbers and distribute this out, 1640 plus 26,732, 28,372 joules already added from earlier. There's 80.0 grams for the ice, 4.184 joules per gram degrees Celsius. Temp final minus 0 degrees Celsius. Well, that must equal negative 90,000 grams times 4.184 joules per gram degrees Celsius times temp final minus 37 degrees Celsius. Let's combine a few things, multiply these and then distribute. Same here, multiply these and then distribute. Let's get the two sides. It's going to give us 20,372 joules to there, plus 334.72 joules per degree Celsius TF. So these two times TF. And those two times 0 will be 0. So we don't do the next part there. On the other side, 90,000 times 4.184 is going to give us negative 376,560 joules per degree Celsius TF plus 139,32720 joules. let's move things to other sides. So I'm going to add this to move it to the other side. I'm going to subtract that to move it over there. 376,895 joules per degree Celsius TF is equal to 139.04348 joules. Now I can divide this on both sides, 37,6,895 joules per degree Celsius, divided by 37,6895 joules per degree Celsius. My joules will cancel, my degrees Celsius will go up. What we'll find is that our temp final is 36.89 degrees Celsius. Without sig figs being concerned, 8919 degrees Celsius, which earlier we'd said it was 37 minus 0.108, so it should have come out at 36.892. And more or less that's what we find. Because we didn't have that many sig figs within the error of our calculation anyways, we don't really notice a significant difference here. 80 grams versus 90,000 grams is an incredibly tiny fraction of the overall mass of the water that's exchanging temperature, well below the 3 sig figs we were working with. However, increase this up to 800 or more, and then it becomes a larger fraction of the total, and the slight error introduced by not setting these equal to each other to find that final temp becomes more significant and more meaningful. But here's how we would do it. With our small amount, it didn't really change our answer too much, but a larger amount, we would need to do this to find the real final temperature of the two things meeting, rather than calculate it all the way up for the snowball going completely to 37 Celsius, despite the body technically dropping below it.